So a couple things here. If you looked at the module for today, the page for today, then you know that tomorrow I don't have anything for you to do. Okay? So you can use that day to get caught up on stuff. You know, if you get chemistry you're still catching up on, use it to get caught up on your chemistry. You know, get all your Lewis structures made, things like that. If you got all your chemistry done, then use it to get caught up on another class. If you're caught up with all of your classes, then binge watch something, play a video game. If it's sunny out, go out and get a little vitamin D. Okay, so yeah. The reason why is because the next stuff that we're going to be covering is better covered when we can talk back and forth. You know, show you some examples, have you guys look at those, and have you ask questions about it. Okay? So, and I need a break. All right? I'm prepping a lot. Okay. So today, we're going to talk about the Vesper activity. Make sure you guys understand a couple things. Go over at least a couple of the first 8 that you did to identify the polarity and see how you did on that, and explain why a little bit more. The video I had you guys watch yesterday with that instructor, I think it was Mr. Key, I think is what his name is, was done really well. That's why I picked it. I didn't have time to create one, but the way that he went through and explained it was really good, and basically how I'm going to explain it. The difference is that we're actually going to have physical models rather than just a picture. Okay? So I'm going to do an example we'll do a couple examples from the Vesper activity, and then I'm going to do at least one example from the Lewis Structures 1 and explain that. But in front of you, before we get started, in front of you, you have a model kit. So at your lab station, or not, at your table, you got a model kit. Okay? Go ahead and open that up. Now, this is the same thing I had in class the other day, but I hadn't had a chance to put these together, and I decided it was time to, go ahead and make some where you guys could actually have some hands-on. Again, it's one of those things. It's one thing to be able to look at it online. It's a completely different thing to actually hold it and see it. It does help to understand how we get the shapes, why their names are the way they are and stuff. Okay? So, I'm going to start off by telling you to use one of the black atoms and put 4 sticks in it. The sticks I want you to use are the shorter ones that are thick. Now you're going to have a model that looks like this, right? Now the reason why I had you do this is because by far, I think when you guys did the finish that grid, by far the most common steric number was 4. Okay? And a lot of the molecules that we're going to look at, a lot of the compounds we're going to look at are going to have a tetrahedral group geometry. So now you got something that you can actually hold and see rather than just having it on a 2-dimensional device where you're just flipping it around. Now, tetrahedral. This is the group geometry. It's the parent of several other different molecular shapes. So, tetrahedral, because if we look at this and you hold it in your palm like this, on your palm is one side, And then you've got 3 triangles you could lay over the other 3 sides. That gives you 4 sides. Tetra means 4. Okay? Now, go ahead and put atoms that are all the same color onto that molecule, like this. So you're going to fill up the other end of those sticks. Now, putting those on didn't change the shape, the basic structure of this at all. And if you go through the document, you will see that every single one of the compounds where you had a steric number of 4 with no lone electrons. So everything was AX4 and your steric number is 4. Every single one of them had the group geometry and the molecular geometry the same. They were both tetrahedral. In the document, pull that up here. For example, I think SiH4. Go look at that. Oh, for crying out loud. Come on, people. Have your stuff out. So in the Vesper theory activity with the grid that you needed to fill out for today, remember the only thing that you didn't fill out was the polarity part. We're going to talk about, well, except for the first 8. I had you do the first 8. This would be SiH4. It would have a tetrahedral group geometry as well as a tetrahedral molecule geometry because all of these are bonds, atoms bonded to that central atom. In that grid, anything that was a steric number of 4, where you had lone pairs of electrons, the name for the group geometry was still tetrahedral because we named the group geometry based on just the bonds and the lone pairs. But the molecular geometry would have been different. So take, we'll do OF2, the one right below that. OF2 has 2 lone pairs of electrons, correct? So take off 2 of those atoms, not the sticks, just 2 of the atoms. And now you end up with something that's going to look like this. Okay? Have we changed the core structure any? No, it's still a tetrahedral. So in OF2, your group geometry is still going to be tetrahedral because it's got a steric number of 4. But the molecular geometry is different. The molecular geometry is naming the shape based on just the atoms. So go ahead and take those 2 sticks off. And now you got this. And if we name that shape, it's going to be the bend. So remember how I said a couple minutes ago that the tetrahedral group geometry is the parent of several other shapes, one of them being bend. Questions so far? All right. Go ahead and put those 2 sticks back in. Put 1 atom back on, not 2, so you've got this. You got 3 atoms, you got 1 stick. This would be like the NCl3, where the white represent the chlorines and the black represents the nitrogen. Again, still tetrahedral, right? But tetrahedral based on the fact that we of the electron groups. But if we look at just the atoms now, definitely different than a bent, okay? It's three-dimensional, and we call this a trigonal pyramid. Because it looks like a little pyramid, and it's got a triangular base to it. Questions? Okay. Okay, so remake the one, just imaginary molecule. This would be SiH4. Okay, so that. And if I remember correctly, if you drew the arrows on these, your hydrogen should be pointing to the silicon. Because silicon's got a slightly larger electronegativity. Am I remembering that correctly? Okay. Now, does everyone understand why I'm drawing it like this? Because this is obviously not a cross, right? It's not, 90-degree angles between stuff. I'm not saying you have to draw them like this. I'm just saying it might help sometimes. All right? So in my structure here, we're going to talk about polarity. There's two different types of polarity that we do what?
I think it's 1.9, so wouldn't it be going outward?
So this is 2.2?
Yeah,
And this is 1.9?
Yeah.
Okay, thank you.
I was confused. I thought I did it wrong or something.
No, my other two classes said it was that.
No, that's not what it says on here. It says 1.9.
So they lied to me.
Yes, they did.
They're just too scared to say the truth.
I've never gotten upset with somebody for correcting me. I appreciate it. I'm not perfect. All right, so it doesn't change anything I was going to discuss, though. We got two different types of polarity. We got bond polarity, which is the polarity of a single bond. And when I say single bond, a single, double, triple, one bond. Okay? Where in our Lewis structure here, we're showing that in this bond between hydrogen and silicon, that there is an unequal attraction and that the electrons are shifted towards the silicon. Well, that means that the hydrogen is going to be a little bit positive. There's several ways of representing that. We can do that. We can put a cross on the end of that arrow. I don't really care. Our primary way of showing the polarity of the bond is just with the arrow itself. So we would say, excuse me, we would say that the polarity of that bond is slightly polar because the difference isn't that big, but there is a difference in electronegativity. So that bond is slightly polar. That means this hydrogen is slightly negative, slightly positive. Now, when we look at the molecule polarity or molecular polarity, and this is what the last column is about in that document, we're looking at overall, does this molecule have opposite sides? Is there an imbalance in the charge and how it's distributed? Now, in this case, every one of these white atoms on this represents a hydrogen. And every one of these bonds between the silicon and the hydrogens, they're all the same thing. So all of these hydrogens are going to be slightly positive, the same amount. Now, yes, I do have positives out here, and I've got the negative charge concentrated around the central atom. But when we look at the molecular polarity, we're concentrating on the outside, around this molecule. Do we have an imbalance in charge? And one way that I do this is I say, okay, can you hold in flat hands anything other than just positives? Try it. Use flat hands. Move it around. Is there any way that you can hold this so you have a positive in one hand and a negative in the other?
No.
No way. Because that negative charge is buried in the center of this very symmetrical molecule. Not just symmetrical in the way that the atoms are arranged, but symmetrical in the sense that they also all have the same charge. Everybody okay? Is doing this, actually holding them, helping?
Yes.
Okay. Now, change out one of these and put a different color. I don't care what color. I'm going to use green. You could use blue. You could use any color you want. You don't have to go see it, but I think it's number 17, unless my last period lied to me. Which, one of the compounds you did was CH3Cl. Remind me, because I've given instructions so often, but also spread out over time. Did I tell you guys to put the arrows in the Lewis Structure 1 and 2 document, or just the Vesper theory activity?
Just the Vesper.
Okay, so you could go back and do, I'm not telling you you have to, but for moving forward, you can, okay? So in the bond between carbon and chlorine, chlorine has the higher electronegativity. So in this molecule now, we've got all of our atoms symmetrically arranged around that central atom. I mean, the only difference between it and the last one we just talked about is we just changed out one atom. But changing out that one atom makes a huge difference. Because instead of having only positives all the way around, now I have positive charges from the hydrogens, and I got a negative charge on the chlorine. Because the electrons between the bond between carbon and chlorine are shifted towards the chlorine. So that makes it slightly negative, whereas the hydrogens are slightly positive. The final little symbol there is slightly. Okay? It's a Greek letter. Don't worry about it. All right, it's delta. Lowercase. Okay, moving on. This is negative. These are positives. Can you hold this so you have a positive in one hand and negative in the other?
Yes.
Well, yes. That's now a polar molecule. And the fact that it has an area, and here's the thing, that area that's negative will always be negative. These areas that are positive will always be positive. They may fluctuate a little bit, but this is always going to be more negative than these are positive. This is going to be a polar molecule. Everybody all right? Yes?
So if it's this, if you can like hold the negative, you say that makes it clear.
If you can separate, make a distinction, and separate the positive from the negative, then you've got a polar molecule. Has anybody, Charles, you're in physics, right?
I took physics.
You took physics. Anybody else take physics already? Anybody in physics? think of this as like vectors for chemistry. Okay? You got, in this instance, you've got a vector going up, but you have 3 equal vectors off at an angle that are completely canceling it out. Whereas now we've got all vectors pointing in and up. There's your difference. Okay? All right, now make SIS2. To do that, though, you're going to have to use a slightly different thing. The bendy, the long, slim bendy sticks. They make double bonds like this. Okay? So you put the 2 sticks in, bend it, and attach the 2 ends to the other atom. So you're going to have to use the black. You could use black and 2 blues, black and 2 yellows. Don't use browns and silvers yet. Actually, we're not going to use those today at all. But make sure the 2 atoms that you're attaching to the central are the same color. Chemistry Legos. Caroline, put 2 more sticks and then bend it to connect them. Does that make sense? Huh?
Oh, I get it now. Okay, so these 2 bottom ones need to go to the blue one, and these 2 top ones need to go to the blue one.
Why doesn't this just represent this just represent 2?
Because,
I mean, like, that was it started, and just like, okay, so here we
but they're like opposite.
You are going to end with something that looks like this.
Why does it have like a weird looking shape to it?
Okay, so
It doesn't look like this when we did it online, so.
no, I mean they use 2 straight lines.
Yeah.
And these models, they're designed to help represent not just how many lines you would have, but also to represent how these things would be arranged. There's also another layer of bonding that we haven't talked about. If you take AP Chem, we'll talk about it a little bit. But this does show a little bit of that where there's, I'm not going to go into details. Okay? But there is a reason why they're going to be like this, and these are kind of rotated 90 degrees to each other. Here's the thing. What shape?
Linear.
Linear. It's a straight line, right? The electronegativities for these, SiS2, they're going out to the sulfurs, right? So they point out. Both of these then are negative. Equally negative because they're the same atoms. And it's going to be nonpolar. Because there's no way that you can isolate and have one part be positive and one part be negative on the exterior. So this would be a nonpolar molecule. Okay? I can't remember. Did we correct the second one, PO4, 3 negative? Or we corrected it to PO4, right?
Yeah.
Okay. So that would have been nonpolar. Because you would have 4 atoms all attached to the central atom in a tetrahedral that are identical to each other. O and F. Go ahead and make that. Actually, take this. I'll make it fast. Take this. Take off those double bonds and single bond another atom. Okay. Now I've put the lone pair on here just to help with visualization. Trigonal planar group geometry, because if you look at it, we've got a triangle here going, right? And if we look at it this way, they're all on the same plane. This is probably the one that the online modeler represents the best. Okay. Now, because it doesn't have an atom here, its shape name bent, because we're just named the shape for the molecule based on just those atoms that are bonded. Remember what I said? If it's got an E in the Vesper notation, the group geometry and molecular geometry will have a different name. Okay? Polar or nonpolar?
It's 2 different negatives, isn't it?
They're 2 different negatives, but is the thing symmetrical?
Yes.
You could, yeah, but it's different.
I mean.
Well, if it's different, it's not symmetrical. Now, you brought up the fact that both of these are negative, yes.
Yeah.
Are they negative equally?
No.
No.
Well, that means one's more what?
Negative.
Than the other, which is more,
Positive.
okay? If both of these are negative, that makes this one in the center what?
Positive.
It's a positive. So, if I hold it like this, do I have distinct positives and negatives? Yes, I do. Polar. Okay. In the end, I'm going to try and make the polarity thing as simple as possible because, again, we're talking about really complex things. We're going to look at relatively simple molecules. But if your molecule is asymmetrical in one way, shape, or form, then it's going to be polar or have some polarity to it. Okay? The CH2Cl2, anyone get a shot at that?
Which one?
The C2H2Cl2, that was the second one on the second page? Polar or nonpolar?
Polar.
Polar. It's asymmetrical. You've got chlorines and hydrogens on there, right? ASH3. Now this one, everybody make this. Henry?
Wait a second, so on the last one, the hydrogens were chlorines, that would be nonpolar.
Correct. That's one we'll probably make next week.
Doesn't the polarity go both ways?
Well, that's what we're going to talk about. So let's start off with this. The lone pair on this is forcing these downwards, right? That's why these atoms are taking the shape that they do. Is this symmetrical? No.
No.
This is different than these down here, right? So it's not symmetrical. But it's not polar either. And that's because if you look at the electronegativities, they are the same between the arsenic and the hydrogen. So you have to have a difference in electronegativity for the bonds to be polar. Here's the thing. If the bonds are not polar, the molecule's not polar. Even though this shape says it could be, it's not. Everybody okay? All right. Just for time, we're going to go on, okay? So I want you guys to, after having had this discussion a little bit, I want you to go through and finish the polarity column for next time. Okay, so it'll be what? Thursday next week. Okay? Usually next time's tomorrow. But remember, we got the same lessons in both days. Okay? So go ahead and put those away so they're not tempting you and playing with them. Now we're going to do a lab. Have you guys heard about this lab yet today? Are you looking forward to it?
Because the slime was really bad.
Who'd you talk to?
Joey.
Who?
Joey.
Joey? His slime was bad? I thought it was pretty good.
Well, he said it was wet, not bad.
Well, I mean,
Well, I think
all slime's wet.
Yeah,
Like,
We're going to make slime. Are you excited about making slime?
sure.
Okay. It's fun. Who made slime in elementary school or middle school?
Yeah.
Yeah. Okay. Shaving cream, borax, food colorings, smelly stuff, yeah, all kinds of, yeah. Glitter. Let me do the glitter part. Yeah, that's a mess. All right, so I don't consider those true slimes. We're gonna make real slime, the original recipe. Okay. So in Drive, you've got a document there for the activity. Because what we're going to do now is now that we've introduced this idea of polarity, if we can identify a material or substance as being polar or nonpolar, how it interacts with other things can tell you about their polarity as well. In general, it's pretty safe to say that nonpolar materials will interact with nonpolar materials. And polar materials will interact with polar materials. And in general, if you have polar materials, they don't interact well with nonpolar. Okay? Now, I'm going to give you two different instructions. These first instructions are meant for Mr. Milligan's class. That's why I'm recording this. Okay? So in Mr. Milligan's class, when you guys do this, you are going to be using a hot plate rather than a Bunsen burner. And I think you also have some different size glassware. I think you have a 250 milliliter beaker versus us using a 100 milliliter beaker. But the procedures otherwise are the same. When you go to heat up your water, you're going to heat it up to about 40 degrees Celsius, maybe a little bit above, a little bit below. If you go a whole lot above, and it won't be hard to do that, then just dump it out and start over again. So if you're in Milligan's room, you're going to have hot plates set up. Just set the beaker on the hot plate for like 5-10 seconds, take it off, and take the stir it around, see what the temperature is, until you get it up to the temperature that you need to be. And then you can continue on with the procedures. One of the things you want to make sure that you do when you are making your slime is, and this is for everybody now, you want to make sure that when you are adding the guar gum to the water, the warmed up water, that you're mixing it very well. I would tell you it's like you're scrambling eggs. Okay, you're going to whip them up, and you want to have as few chunks of the guar gum as possible. So you want to put, as you're stirring it, you want to put a little bit at a time. Stir it, put a little bit, stir it, put a little bit, and as you're, since you got two people or possibly three, they can pour it in while somebody's stirring, so you avoid those clumps. Okay. Now, for you guys that are in front of me, you're going to be using a Bunsen burner. And I will tell you, it's actually a little bit harder to control that than on a hot plate because the Bunsen burners are really hot. So you just use crucible tongs. The tongs are in your top left drawer. You're going to hold the 100 milliliter beaker with the water over the Bunsen burner for like maybe 3 seconds. Take it out, take the temperature. I know right now the instructions say 30 degrees Celsius. I'm changing that to 40. I'm verbally telling you 40 degrees Celsius. I need to go and edit that. Okay? Once you've got it up to that 40 degrees Celsius, a little bit above, a little bit below is fine. Then you're going to add your guar gum, stir it. Then you're going to do the borax, stir it, whip it, and you're going to have your slime. Okay, it'll be perfect slime if you follow the instructions. Now, once you have made the slime, you're going to use it to test the polarity of different things. Now, let me grab one real quick. Back at your lab station, borax, obviously labeled borax. In Milligan's class, I think a couple of the bottles may not be labeled. My label maker broke, dead, can't start it up. So bottle with liquid, borax. Bottle with powder, that's your guar gum, okay? You're going to have, oh man, idiots. There should be a spoon in here. So you're going to have a baggie that's going to have all the supplies that you're going to do the testing with. When you're making your slime, you can use the spoon that should be in here to measure out your guar gum. When you go to measure out your borax, you can use the pipette to help get it to the 5 milliliters. So if you pour 5 milliliters, if you pour like 6 milliliters into the graduated cylinder rather than pouring it out, just suck it out with this and you get it perfect. If you put in like 4.5 milliliters and you gotta get a little extra, put drops in until you get to 5. Okay? So you can use this to adjust your borax. I don't think it's in the procedures, but you want to use, you're going to use all of the writing utensils to test the polarity of the slime in a silly putty. You also have some newsprint. Okay, you want to test those with the slime and the silly putty as well. If you scroll down to the bottom of the lab, you're going to see that you have a grid of places where you can put your observations. Like what's the material, the substance. So just put like the pen. What pen did you use? What was the brand name or something like that? Was it newsprint? And then you'll make the, the observation about did they interact? Okay? When they interact, what you'll see is that you'll see that the slime or the silly putty will actually lift off with some of the inks on them. So that would be an interaction. Okay? After that, you're done. Just clean up, put everything away. Okay? Questions? All right? Let's see here. You guys worked together last time, right? So you're working with those guys. You were both here last time. And you, all right, we're good to go. Go.